So another form of writing the solution to the differential equation or the general solution of the antiderivatives is through writing integral here f of x dx. This is a solution that you might be familiar with back in high school. So usually this symbol here represents the integral or the antiderivative function. Then we have f of x, which is the function that we are trying to integrate or find the original function of. And then d of dx is just this just represents the variable that we are trying to integrate on. So for instance, since we have x here, we'll have x here. Had we had z, f of z, we'll have d of z here, and so on. This is the same for this is the same as f of x plus c. They are equal because if when we integrate f of x, we find the original function f, which is the antiderivative of f of x plus the constant c. So the relationship between integration and differentiation is like an inverse relationship. What I mean by that is that integration undoes what differentiation does, and differentiation also undoes what integration does. For instance, if we have f of x, and then we try to differentiate this equation, we'll end up with f prime of x. Then what if we try to integrate that function? So let's say we do the integral of f of x dx. We'll end up again with just f of x. So it's like we went back to the original function that we had here. So this also this will be similar in case we just had integral of f prime of x. It's like the integral here undoes what this derivative does, and we just get the original function. It would be the same the other way around if we had, let's say, integral of f of x, and then we do the derivative, we'll just end up with f of x again. You can also see the relationship between integration and differentiation as going to the future or going back to the past. So let's say we have the function 3x squared. So if I were to differentiate this equation, we'll end up with 6x. But if I were to go back to the to integrate this function, we'll end up with x cubed. So going to the future, to go into the differentiating this function here is like going to the future. It's like asking, what will this function look like if I were to differentiate it? And on the other hand, if I were to integrate it, it's like asking, what was the function that I had in the past before getting to this function here? So it's like going to the future or to the past. That's one way of looking at it. So earlier we said that g of x equal to f of x plus c is a general solution for the function f of x, or is a general solution for the antiderivative of f of x. This general solution here is also called the general solution for the antiderivative. The general solution for the differential equation is general solution for the differential equation. What I mean by the differential equation is I don't know if you know it, but generally speaking, a differential equation is an equation that involves both the function f of x, and its derivatives. So let's say if we have f of x plus f prime of x plus f second prime of x plus tan until, let's say, f of to the f to the nth derivative of x equals, let's say, equals to 2 or something like that. This is a differential equation. It involves f of x, its first derivative, its second derivative, up to its nth derivative. We don't usually have all of these derivatives. We may just have f of x equal plus f prime of x equals to 0. This is also a differential equation. Even f of x equal to 3 is a differential equation. So in this differential equation, we are trying to find the solution. Well, usually we have f of x, f prime, f second prime, and things like that. And we are trying to find the original formula for the function f, which is f of x. So the solution we usually find is the general solution. And that's also what we called general solution for the antiderivative of f of x. And that's f of x plus c that we found earlier. Why is that important? Is because when trying to find, let's say, y in this example right here, we are also trying to solve differential equation dy over dx equal to 2, which is also the same as saying we are trying to solve f prime of x is equal to 2, and we are trying to find f of x, the value of f of x. We are trying to find f of x. So let's try and do this example here. We had dy over dx equals to 2, which is similar to, let's say, dy over dx is equal to 2, is similar to f prime of x equal to 2. Then what would be an original function for this f prime here? Well, surely it will be something like 2x, right? Because the derivative of 2x will be 2 plus a certain constant. Why? Again, because we are trying to find the general solution for this differential equation here. And this is the solution for f prime of x is equal to 2.
Now we can start talking about how to find antiderivatives, or how to find that original function that we are searching for. Usually, in the exercises we've done so far, we try to find that uh, original function using intuition, but intuition won't always give us the right answer. So this is where the basic integration rules comes in handy. So what the basic integration rules says is that it gives you a bunch of rules that you need to follow in order to find to integrate a certain function. For instance, if we were to have, let's say, a function c, the derivative of a constant is just 0, right? Then the integral of that 0 will give us a constant. Or why? Because we are trying to find the original function, and then the original function is this c here. If we look here, we have the derivative of k of x will be k, whereas the integral of k is just k of x, because we just return that x that we removed from differentiation here in integration plus a certain constant. It's the same here. The derivative of k times a function is just k times the derivative of that function, which is k times f prime. Then the integral will also be the same. We can take the constant out outside of the integral, and then we just integrate over f. The sum of two functions in a derivative will by, let's say the derivative of f of x plus g of x will be f prime of x plus or minus g prime of x, and that will be the same in the case of integrals, because we'll have the integral of f of x plus g of x will just be the integral of f of x plus the integral of g of x. The derivative of a power function is say x to the power of n is just n to the power x n minus 1. We just let's say we reduce the power n by 1. In other words, that if we were to go through integration, which is the inverse of differentiation, instead of minus 1, we need to add plus 1. So the derivative of x to the power of n will just be x to the power of n plus 1 over n plus 1 plus a constant. Why? Because let's say we want to prove that this is really the function that we are searching for. We just differentiate this. This will give us, if we were to differentiate x to the power of n plus 1, it will be n plus 1 times x to the power of n, and then n plus 1 will go with this n plus 1 here, and then we'll end up with just x to the power of n. Um, Now let's go to the sine, cosine, and all trigonometric functions that you need to know. So sine x, the derivative of sine x, as we know, is cosine x. So in other words, the integral of cosine x is just sine x. We go from here to here. A good way to remember that is that to let's say you remember how to differentiate such functions, and then the result of that function will usually be the one inside the integral. So you just need to remember what you did. Let's say that you had integral of, let's say, sine x, and then this sine x, you can think of it as the result of an integral of a differentiation that you did before. So what shall I differentiate to find sine x? Well, cosine will give me minus sine x, so I just need to do minus cosine x. That's what is said here, because the derivative of cosine x would be equal to minus sine x. Then this also means that if I want to integral of sine x, I need to do minus cosine x. And then we keep going throughout all um, the the formulas here, the rules that you need to know. Just tangent of x is just secant square, and then vice versa. If I had secant square inside the integral, it will just give me tangent